Welcome back, students. Just a little bit more computation and we are going to be done with section 1. Eigenspaces. We're doing this, and then what did it do? We found out eigenvalues 0, 1, and 2 from this example. And how did it do that? By characteristic equation. And solving this polynomial equation is a tedious job, but it is possible. So if you do that, you're going to get 0, 1, 2, and another 2. So these are the eigenvalues coming from the fourth order polynomial equation. Now for the simplest case, lambda equal to 0, we just set up characteristic equation, basically a v equals to 0v, set it up, and v is xyzw, and then just do your computation. Do some elimination and substitution, and then after some trouble and time-consuming computation, we got this, and we can write it as a scalar multiplication of some scalar times a vector, so it's one-dimensional subspace. You can do the same thing for lambda equals to 1. Again, it's going to be one-dimensional subspace if you do it. And how do I know it's one-dimensional subspace? Actually, there was no duplicate, so I know it's one-dimensional. That proof will be done in the next section. Now, how about for lambda equal to 2? That's going to be harder because there was a duplicate. And we went through the solution very, very quickly. But probably that was not even enough for a lot of students. So let's do this again. Okay. So we are done with this one. And then I'm going to leave this to students. Let's do this part. Okay, how to do this? X, Y, Z, W is twice of this. That's what we want. Okay. Oops. Okay, let's do this matrix multiplication here. Negative 4x minus 2y plus 0z minus 2w equals 2x. Here we have 2y, 2z, 2w, all those, that's easy. Left hand side, let's go to the second row. This times that. So this is 6x plus 4y plus 0z plus 2w. And this one is going to be negative 6x minus 2y plus 1z minus 3w. 6x plus 2y plus 0z plus 4w. And this is what we have. I hope I did everything correctly. Is everything right about matrix multiplication? Okay. Let's copy and paste this thing. And then subtract. Subtract, and that's 0. Subtract, that's 0. Subtract, that's 0. Subtract. So what did I do here? Subtract right hand side from the left hand side. Subtract 2x, 2y, 2z, and 2w respectively from first, second, third, and fourth row. No problem there. And then some further simplification. Okay, all right. From the first row, everything is even, so simplify by dividing everything by 2. Okay, we get that. And all even here as well, so dividing everything by 2. All even here as well, so divide everything by 2. And I can simplify here, so let's leave it and let's move on. Whoops, what did I do? I didn't want to create this big a duplicate. Okay, all right. First and second row, they're basically identical. I can simply add second row to the first row and then I get 0. 0 equals to 0, no problem there. Second row and fourth row, they're the same, so I can simply, subtract. So we have fourth row and third row. Okay, let's do some work here. Now, can we solve for one of the variables here? Yes, I guess I can do that. From the last equation, which I'm highlighting in blue, looks like I'm getting w 3x plus y plus w equals to 0. So w is equal to negative 3x minus y. Is that correct? So okay, let's put it into the second equation, a third equation, excuse me. Negative 6x minus 2y minus c minus 3w equal to 0. And I'm plugging in here negative 3x minus y. Does it look okay? Alright, let's do some simplification. Negative 6x minus 2y minus z, and then plus 9x plus 3y equal to 0. I hope my computation is correct. And then 9 minus 6, 3x, and then plus y minus z is equal to 0. I'm getting z equals to 3x plus y. Okay, looks like everything is correct. So therefore, can be written as, let's see, x, y, and z is 3x plus y, and w as negative 3x minus y. You can write it like this. And then, well, okay, because we proved that set of all eigenvectors, including the zero vectors as well, form a subspace, we can declare that this would define the subspace. X, y, 3x plus y, negative 3x minus y, where x and y are real numbers. This is actually a correct solution. but it may be a little bit difficult to see that this is a subspace. Can you actually see it? Everything's linear, nothing, no second order, and then no constants. So to me, it is clear. So this is subspace, and you can actually prove it. But in case there are some students who are having a little bit difficulty seeing that, let's have a little bit further computation here. This can be rewritten as, let's see, x 0, 3x minus 3y, 3x, sorry about that, plus 0, y minus y. Can you see the decomposition? All the x part here, or the y parts there. So I have x only here, so go to x and nothing in y part. Y here, nothing here, y goes over there. And we have 3x plus y, 3x here, y here, negative 3x minus 3y, negative 3x here, negative y here. Do you see it? Then this can be rewritten as x times 1, 0, 3 minus 3. And this can be written as y, 0, 1, 1 minus 1. What did we end up with? We ended up with a linear combination of two vectors, 1, 0, 3, 3, and 0, 1, 1, negative 1, which you can prove as linearly independent. I mean, if you have just two vectors, then it's easy to see whether those are linearly independent or not because they're not collinear. You can see that one vector is not constant times another vector, so it's easy. If you have three or more, then the proof is harder. So you can rewrite this V2 alternatively as follows. Set of these linear combinations where x and y are real numbers. Or you can write like this as well. Set of all linear combinations, all right? So that's basically a subspace generated by these two. So you can write like this. So there are many equivalent forms. Once you get the solution, two characters, put those together where x and y are moving around for arbitrary real numbers, and that's one way to write the final answer. But this is not the most favorable method that our textbook author uses. I like it because it's simple. Our textbook author prefers to get simpler vectors like this and that, and then how to get those vectors. We talked about those in previous video when we get eigenvectors, not determining the eigenspaces, just eigenvectors, and then just express it as subspace generated by those eigenvectors, and that is the eigenspace, and that's a preferred method our textbook author uses. In any case, it'll work. So let's go back here. Set up the system of linear equations basically. Matrix times the vector is eigenvalue times the vector, and then set up the system of linear equations. It took some time solving it because, what can you say, there are four unknowns and four equations. It's complicated, but you can use some eliminations if you do it right. If you don't make any silly mistake, you can remove some equations. It'll turn out two equations are gone. We have four unknowns and two equations. We're down to those. So we can determine only 2. So 2 are running freely. The other 2 are determined by the other 2. So we are talking about 2-dimensional subspace. 2 degrees of freedom. 2 characters are moving around freely. Here, according to this, W is solved by X, Y, and Y, and Z is solved by X and Y. So X and Y, 2 characters are running freely. So we have 2 degrees of freedom, X and Y are running freely, and that forms a subspace. Or you can plug in X equals 1, Y equals 0, and vice versa, X equals 0, Y equals 1, get 2 vectors, which will be this one and that one respectively. Go back to previous videos if you want to make sure all those. And then you can write as the set of all linear combinations generated by those 2 eigenvectors. In any case, it'll work. So we went through eigenspaces, and we did the same problem in different viewpoints multiple times. So I think we covered reasonably thoroughly here. Let's complete this section by one more theorem, which we'll not prove here. If you have distinct eigenvalues, then let's see. Okay, all right. Let V be a vector space and let L be a linear operator, and we have M distinct eigenvalues, lambda 1, lambda 2, lambda 3, all the way over to lambda M, and V1, V2, V3, all the way over to Vm are eigenvalues of lambda 1, lambda 2, all the way over to Lm. Then they are linearly independent. So eigenvectors of distinct eigenvalues are linearly independent. What if you have duplicate? That's going to be a problem. In this case, let's go to the previous example. What if you have duplicates? That's going to be a problem. In this particular case, we found out 2 distinct eigenvectors that are linearly independent, but not always. Sometimes things don't go as well. Fortunately, however, from this point on, you're going to focus almost entirely upon distinct eigenvalues, so you don't have to worry too much about those. Even when we have duplicate, we will consider only those eigenvectors that can be found. I mean, linearly independent eigenvectors could be found so that we get basis consisting of eigenvalues. We'll consider only those kind of cases. In general, things can get really hard, really deep, really quickly. Okay, a brief summary again. We talked about linear operators, all right? We talked about eigenvectors. L of V is lambda times V. That's eigenvector as long as V is non-zero. And that lambda is eigenvalue. Now, how do you find eigenvalues? Through characteristic equation. Where's the characteristic equation? This. And if you have 3 by 3, then third degree. If you have 4 by 4, fourth degree equation, and so on and so forth. For each characteristic value, for each eigenvalue, you can find out eigenvectors. And then get linear combinations of those eigenvectors, then you get eigenspace. That's where we're going to stop.